right, so we're going to talk about Jacobians, changing variables.
Actually, yeah, this is actually why.
When do you tell people? Once you go to the they're like, oh.
Crazy amount. Hey, what did the rate? What's the next one? Status.
The intervals?
Yeah. Crazy. Oh wait, interval sounds less fun than calculus, which is the same. It's just that it's not, because this one is just intervals.
All right, let's get started, guys. So we're going to talk about how we change variables in multiple integrals. So to kind of motivate it to start off, we're going to remember how we changed variables in single integrals. So in single variable calculus, we used U substitution, our favorite integration technique, right? So in U substitution, we had we used U substitution to simplify integrals. So for example, if we had some integral from a to b of f of x dx, and x is some function of u. X is g of u. So dx, I'm just kind of writing out the procedure for U substitution, or motivation for U substitution. Dx is g prime u du. Or we could write dx is dg du times du. And if we put this back into our original integral, our integral becomes the integral from a to b of f of x dx becomes, after we change our variables, the integral from c to d of f of g of u times dg du du. And a is g of c, and b is g of d. So this is kind of a drawn out example of how we change variables in a single integral. Now what changes is I just want to look at the form that we have here. We have this factor. We have our function becomes a function of our changed variable, and we have this factor that involves a derivative of some function of the changed variable, and then our derivative is with respect to our new variable. So this is how we make a substitution, how we change variables in a single integral. We can think of U substitution as changing the integral to the variable u. We're changing the variable of integration to u to make the integral more simple. We can do a similar thing in double or triple integrals. This factor with the derivative takes on a little more complicated form, as we might expect. So if we change variables in a double integral, or for multiple integrals, if we have the integral over some region of f of x y dA, we'll look at double integrals for now. We change variables. We let x equal some function of u and v. And y also equals some function of u and v. So we're making, instead of x and y, our new variables are going to be u and v. Our new integral The transformed integral is the integral over S of f of our new variables, g of u and v, and h of u and v. Those are our new variables, times this quantity dx du dy dv minus dy du, partial derivatives, dx dv. And I need a little more room. And my variables of integration become du and dv. So this is similar to our dg du in u substitution, this quantity. And S is the region for after the change of variables. And the reason that we'll change variables in multiple integration is if we have a complicated region. So if we have some region where we end up having to break the region up into multiple parts, or if we have a complicated integrand and we can make a substitution to simplify the integrand, would be the reason that we would change the variables. Just like we do in single variable calculus, where we have a difficult integrand, we change variables, use substitution to make our integral doable. Now we call this factor with these derivatives the Jacobian. So dx du dy dv minus dy du dx dv and it's our factor for changing variables. And we say it's the Jacobian with respect to x of x and y with respect to u and v. And we usually write it this form. Looking at this, does this remind you of anything? The form of this thing.
Oh, the product rule.
What?
Almost.
It kind of looks like the product rule. And what did you say, Scotty? It's a minus. So what gives you, what kind of thing do you do with variables where you're mixing the x and y and the u and v and you have a minus in between? Like it looks kind of like a cross product. And what do we use to simplify evaluating cross product? What kind of notation do we use? What arrangement do we put them in? A matrix. So this is like a determinant. So we write the Jacobian as, it has a funny symbol kind of, dxy duv, and it's the determinant of, it's this determinant, dx du dx dv dy du dy dv. And sometimes you will also see also written J sub t of u and v, or just j of u and v. So just different notations. So this is the Jacobian transformation, or just the Jacobian. Now the way we think of this, the way we think of this transformation is we're transforming from the xy plane to the uv plane. So we're making a transformation from one set of coordinates, one coordinate plane, to another coordinate plane. So we're transforming from the xy plane to the uv plane. And one example of where we do this is in polar coordinates. In polar coordinates, our transformation, our change of variables, in polar coordinates we say that x equals r cosine theta, and y equals r sine theta. So that's our transformation. And our Jacobian for polar coordinates turns out to be r. Because when we transform our double integral in polar coordinates, our integrand turns out to be whatever our function is, r d theta. So our Jacobian in polar coordinates is r. If we did this determinant with these transformations, our Jacobian would turn out to be r. So polar coordinates is one example of where we could apply a Jacobian to change our variables, and the r comes from the Jacobian, finding the Jacobian with this change of variables. So what I want to do is do a couple of examples of using a Jacobian, when we might want to use a Jacobian, and then at the end I'll kind of sketch, not a proof, but I'll give some motivation for why the Jacobian takes this form when we want to transform coordinates. So any questions about the kind of the procedure, what we're talking about with the Jacobian? Okay, so let's calculate a couple of Jacobians, and then we'll do an integral or two where we use a Jacobian. All right. So if we want to find the Jacobian for x, we're changing our variables. X equals minus one half u minus v, and y equals 1/2 u plus v. And we'll do an example where we use a transformation like this and explain why this type of transformation comes up. So we need our partial derivatives. So dx du is minus 1/2. Dx dv is 1/2. dy du is 1/2. And dy dv is 1/2. So our Jacobian is this determinant, minus 1/2, 1/2, 1/2, and 1/2. And I just get minus 1/2. So if I were doing some kind of multiple integral and we were changing the coordinates, my integrand would have a factor of minus 1/2 in there, along with the du and dv. So the process of calculating Jacobian, pretty straightforward. We just calculate our partial derivatives and put them into this determinant. So let's look at one that's just a little more complicated. Any questions before we move on? And then we'll do an example where we actually do an integral. Okay. So for this one, our transformation is x equals e to the u sine v, and y equals e to the u cosine v. And we want to find our Jacobian. So our Jacobian, let's just plug our partial derivative straight into our determinant. So du or dx du. E to the u sine v, dx dv, e to the u cosine v, dy du, e to the u cosine v, and dy dv minus e to the u sine v. And when we take this determinant, we get that this is minus e to the 2u sine squared v minus e to the 2u cosine squared v, and that equals minus e to the 2u. So if we were doing an integral and we were using this change of variables, we would have this factor in the integrand. So finding the Jacobian is fairly easy. Let's look at an example of using a Jacobian to actually evaluate an integral. All right. So let's say we have an integral over a region of 60 xy dA. And our region, we sketch our region here. Our region is this parallelogram. And I know it's not a perfect parallelogram, but let's label my coordinates that I want here. This is 0, 1. This is 1, 2. This is 2, 1. And this is 1, 0. And it's a diamond. And my region is in here. So if we were going to evaluate this integral using rectangular coordinates, we would have to, if we used vertical rectangles, from 0 to 1, we would have to integrate between these two boundaries, and from 1 to 2, we'd have to integrate between these two boundaries. So we'd have to switch boundaries. We'd have to do two multiple integrals to evaluate this integral over this region. So if we change our variables, we can use one integral over a transformed region. And the transformation we're going to use here is x equals 1/2 u plus v, and y equals minus 1/2 u minus v. Now, some of the problems in your homework, if the problems are nice, they give you the transformation. But let's look at these transformations and figure out why they might look the way they do. Does anybody have an idea of why we might use these transformations? No? All right, let's look at the equations of the lines that make up the side of this region. The equation of the line for this that goes through this segment is x minus y equals minus 1. The equation for the line on this boundary is x minus y equals 1. On this boundary, the equation is x plus y equals 3, and on this boundary, x plus y equals 1. So we look at the boundaries to motivate our change of variables. So if I say, for example, u equals x minus y, if I make the substitution u equals x minus y, u is varying from minus 1 to 1. And if I say v is x plus y, v is varying from 1 to 3. So if I make the substitution u equals x minus y and v equals x plus y, u and v are varying between two constants. So if I look at the boundaries for this particular example, look at the boundaries to motivate my transformation. If I say that u, make the substitution u equals x minus y, and v equals x plus y, and if I solve this system for x and y, I get these two equations. So the boundary of my region is what motivates the change of variables. Now, if they give you the change of variables, you don't have to go through this process to figure this out. I find this a little easier, just looking at the boundaries. But if you solved these equations for u and v, you would end up with this system of equations. So this system of equations comes from this system of equations. But the boundary is what motivates this substitution. So now we need to find our new region. So with this substitution, we want to transform the region in the xy plane to the region in the uv plane. So in the uv plane, we could make a table of values, we could make a chart to figure out the vertices of our new region. But just from looking at this, we can figure out what our region is. So let's sketch our uv plane. This is v and this is u. We said that v is going to vary from 1 to 3. So here's v equals 1, and here's v equals 3. And we said u is going to vary from minus 1 to 1. So here's u equals minus 1, and here's u equals 1. So this region is my region in the uv plane. So I figured that out just by looking at my transformation here. The other way that we could do it is make a chart and plug in my vertices and use the substitution here that u equals x minus y and v equals x plus y to find the corners of the new region. So what this transformation has done is take this parallelogram and turned it into a rectangle with the sides parallel to the coordinate axes. So it makes the integral a lot easier to do. Does everybody follow how I found the boundaries of my new region? Yeah? All right, now we're ready to do we're almost ready to do our integral. Now we need to calculate our Jacobian. We did a substitution. We need to find our Jacobian. All right, so our Jacobian dxy duv is our determinant, and we need dx du is 1/2, dx dv is 1/2, dy du minus 1/2, and dy dv is 1/2, and that determinant comes out to be 1/2. So finally, my integral, I can transform this integral with the change of variables. Go up a little bit more. I get that the integral over my region of 60 xy dA equals the integral of 1 to 3, v equals 1 to 3, u equals -1 to 1 of 60 times x is 1/2 u plus v, and y is minus 1/2 times u minus v times our Jacobian, which is 1/2, and our new variables of integration, du dv. And this simplifies to the integral from 1 to 3, integral minus 1 to 1 of minus 15. I think I need one more parentheses here. What's that?
Before the 1/2?
Uh,
Because the x and y are together, but the 1/2 is not in there.
yes, before the 1/2. Thank you. There we go. Minus 15 times u squared minus v squared times 1/2 du dv. And this is an easy integral to evaluate. And when I evaluate this out, I end up with 120. So with our change of variables, we transformed our parallelogram into a rectangle with the sides parallel to the coordinate axes. And my integral, I end up with one integral that's easy to evaluate. Now, with these regions that are relatively simple, the substitutions are, they do take a lot of work. They take a little bit of effort to do the substitutions. But if you have a region where the boundaries are more complicated, if you had, for example, if we wanted, I'm not going to go through this example, but I just want to give it as an example of a region with more complicated boundaries. Anybody, any questions before I move on about what we did here? Okay. A region with more complicated boundaries, if we had something, for example, that our region is between xy equals 1 and xy equals 4, and y equals 1 and y equals 4. So this region is a little more complicated. If we sketch this out, we get something like these hyperbolas, and our region is in here. So this region would make the integral a little more complicated to do. And for this one, we would use the transformation. We would say xy equals u based on the boundaries, and y equals v. So if we made this substitution, that would turn this region into a rectangle. So this is an example of a region with boundaries where the original integral would be very complicated. A new integral would be less complicated using the Jacobian to transform this. And the other example, another example of how we would use the Jacobian would be if we have a difficult integrand. So if we had something like, rather than transforming the boundaries of the region, if we had an integrand we had something like this, 0 to 1, 0 to 1 minus x of the square root of x plus y times y minus 2x squared dy dx. So our region in this particular integral is fairly straightforward. Our region is here. So our region is not difficult. This is x plus y equals 1. So our region is easy, but the integrand is difficult. This would be a very difficult integral to try to perform. But if we made the substitution, u equals x plus y, and v equals y minus 2x, that simplifies the integrand considerably, and it makes this integral actually doable. So this would be an example of where we'd use the Jacobian, use a change of variables to simplify an integrand rather than to simplify a region. And the form of the integrand is what suggests this change of variables. Just like we do in U substitution. Questions on that? All right, let me give you a little motivation for why the Jacobian looks the way it does. So what we're doing with the Jacobian is we're taking a region in one plane and transforming it into another plane. So let's look at, we're going to look at a small rectangle in the UV plane. So here's my rectangle. And we're moving, as we move from this point UV, we're moving a small distance delta v and a small distance delta u in the UV plane. So the coordinates of the corners of this rectangle in the UV plane, this one becomes u plus delta u, comma v, and we're moving up a small amount delta v, so this is u plus delta u, comma v plus delta v, and this is the coordinate of this vertex is u v plus delta v. So we're going to move this rectangle into the xy plane. So in the xy plane, this has some shape that is less desirable for performing a multiple integral. So let's say our sides look something like this in the xy plane. So this is why we did our transformation from x and y to u and v. And what we're going to do is very similar to what we did with when we came up with our formula for surface area. We're going to draw a tangent vector right here at this corner of the region in the xy plane. So there's a tangent vector, and we're going to call that one T1. And here's a tangent vector to this side, and this is T2. And our two tangent vectors, we can find our tangent vectors with the derivatives of x and y with respect to u and v. Just like we talked about when we talked about surface area, we approximated this curved surface with a tangent plane, and we took the rectangles or the tangent vectors to the corner of the tangent plane to find our area of our little piece. So we're going to write an expression for the tangent vectors. So T1, as we move from u to u plus delta u, and as we move from v to v plus delta v, T1 is going to be approximately dx du delta u plus dy du, or this is my I component, plus dy du delta u in the j direction. So that's, as I move from u to u plus delta u and v to v plus delta v, my tangent vector is approximated by this expression. That's what gives me the components of my tangent vector. And T2, similarly, we're moving in the y direction, so we're moving in the v. It has to do with the change in v, is going to be dx dv delta v is my I component, plus dy dv delta v is my j component. And we're going to approximate the area of a little parallelogram with the magnitude of the cross product of these two vectors. And we're going to sum over the entire region. Just like we did for surface area, we're approximating the area of a tiny little parallelogram with the magnitude of the cross product between T1 and T2, and sum over the area as delta U and delta V get very small. So the area is approximately T1 cross T2, the magnitude of T1 cross T2, which is the magnitude of this cross product is the determinant of dx du times delta U delta V. And we sum over the region of these, over this entire region to get our result. So the Jacobian takes the form that it does because we're using an argument similar to what we did for surface area and finding the area of this region by approximating with a cross product. Questions? All right. There'll be one Jacobian on the test because it takes a fair amount of calculation. So your take-home portion is going to be your Jacobian. So homework. There you go.